Welcome back to Module 11 of COM 3073. We're going to continue our discussion on experiments by talking about true or classic experimental designs. Recall the discussion from our last module where I told you that experiments are one of the few ways in quantitative research methods where we can assert a causal relationship between an independent variable and a dependent variable. This is because in well-controlled experiments, we can determine time ordering and covariation, but most importantly, we can remove the effects of lurking or potential confounding variables. Unfortunately, in quasi-experiments, those confounds can still exist, so it impedes our goal of claiming causality. In true experiments, however, we can make stronger causal claims. So now that we have the groundwork for today's discussion, let's get into the specifics of true experiments. Here's a review from our last module and part 1 of experiments. Remember I talked about the differences between quasi-experiments and classic or true experiments. I told you that quasi-experiments resemble true experiments, but the major difference is how participants are assigned to the conditions. In quasi-experiments, participants are assigned to manipulated conditions not at random. So, if for instance, I wanted to study the effects of online versus offline education on student motivation, and I chose to study motivation in online education at an online-only university, but I chose to study motivation in the offline education condition at UTSA, this would be an example of a quasi-experiment because I'm using pre-existing groups based on convenience and practicality. But is the academic motivation of these two groups exactly the same? We can't guarantee that, so this is why we call it a quasi-experiment. In true or classic experiments, the assignment of participants to experimentally manipulated conditions of the independent variable is made at random. So herein lies the major difference between quasi-experiments and true experiments. I previously pointed to the idea of random assignment a number of different times, but let me explain what I mean by it. Random assignment or randomization is a technique to assign participants or units to different conditions or groups at random so that each participant has an equal likelihood of being assigned to the control or experimental condition. We do this, of course, because we understand that our pool of participants, represented here by dots of different colors, is heterogeneous in many different ways. In particular, we want to randomize people's pre-existing or state levels of the dependent variable, so we come out with roughly equal groups. But we also randomize groups to even out all the other potential confounds that may be lurking within our group of participants. Random assignment can be easily done by using a random list generator or even flipping a coin. So for participant 1, a heads on a coin could mean this person is assigned to the control group, or a tails could mean that he or she is assigned to the experimental group. You do this until everyone in your main sample is either in the control or experimental group. Matching is similar to stratified random sampling, but on the micro level. You match members on some characteristic important to your study, and then randomly select from within those subgroups. So, if gender balance is important in both groups, because that could be a potential confounding variable like it was in the violent video game study, then you would put all participants into either a male group, a female group, or even possibly a non-binary group, and then randomly assign participants from within those groups to either the control or experimental group. I of course spent time talking about randomization or random assignment because it's fundamental to experiments. By randomly assigning participants to groups, we make an implicit assumption that the groups are pretty much equal across all different variables. Of course, it's impossible to make them exactly equal, but it's the best way to make them as equal as we can. The equality of groups here is represented by the rainbow boxes, and that's meant to signify that the control group is roughly equivalent to the experimental group. In the classic or true pretest post-test design, we give both groups a pretest measure of the dependent variable. So, if I wanted to see whether writing love letters to a romantic partner causes reduced stress, I would administer a stress measure to participants in both the control and experimental group before the experimental group is asked to write the love letter, while people in the control group could engage in a general writing exercise that takes them roughly the same amount of time. After the experimental group is given the manipulation, both groups are given the same stress measure as the post-test. This is the basis for the classic pretest post-test design. However, there is one small problem with this method that researchers have come to realize. That is, if you give participants a pretest measure like mood or stress, they're going to have heightened or unnatural awareness to the stress or moods during their manipulation, which could erroneously affect the responses in the post-test. We call this pretest sensitization, and its existence could contaminate the results. So we have to look to other methods to avoid this pretest sensitization. That's where we arrive at the post-test only design. If we make the implicit assumption that the control group and experimental group are equal after random assignment, then why do we have to administer the pretest in the first place? After all we truly care about is whether there are statistically significant differences in stress or swear words or any other dependent variable between the control and experimental conditions. Most studies employ this post-test only design to avoid the pitfalls of pretest sensitization. All it does is it removes the pretest and goes directly to administering the manipulation to the groups. You then ask participants only once to complete a measure of the dependent variable as the post-test and then look for differences. There is one problem with the post-test only design that I wanted to mention. That is, even if we find statistically significant differences on the dependent variable between the controlled and experimental groups, without a pretest, how do we know if one group rose on the dependent variable or if the other group fell from their baseline? Let's go back to the stress and love letters example from earlier. What if I conducted a post-test only design and found that people in the experimental condition were much less stressed than people in the control condition? Can I say that this confirmed my hypothesis that love letter writing reduces stress of the writer? Well, not really. It could have been that the general writing assignment you had the control participants do really stressed them out. Let me make one other quick note about experiments and observations, which I think you'll find helpful. In 1924, Henry Landsberger was commissioned by the Hawthorne Works Company in Chicago to do an experimental study on worker productivity and lighting in the working area. In the experiment, Landsberger manipulated the conditions such that in some cases the lighting was very dim, and in other cases very bright. What he found baffled him. As expected, when the lighting was high and everything was clearly visible, workplace productivity went up. When lighting was dim, however, Landsberger found that workplace productivity also increased. He found this consistent finding over the course of the 8 years the study was conducted at Hawthorne Works. He also observed that after the study ended, productivity decreased precipitously. So what was the cause of the changes in productivity in both conditions? The increased productivity was credited to the increased attention on workers who were being observed as participants in the research study. We call the better performance of participants as a function of being in a study the Hawthorne effect. It's also why in clinical drug trials, we have to give some patients a placebo or sugar pill to rule out self-reports of better health from being participants in a study. So, as you can see, we have some inherent problems with the pre-test, post-test designs concerning pre-test sensitization, and we have some issues of interpretability regarding gains or losses from baseline scores on a dependent variable with post-test only designs. The solution to this, if you have an incredible amount of time and an endless bank of cash, is to conduct a Solomon 4-group design, which is the gold standard of experiments. It's combining the pre-test post-test design with the post-test only design to get an experimental model with 4 groups. In the Solomon 4-group design, you can rule out pre-test sensitization, but at the same time you can see whether participants' scores on the dependent variable increased or decreased from their pre-test baseline. It's important to note that the Solomon 4-group design is very rarely done in science. That's all I have for Module 11. Please don't forget to read the textbook pages listed in the syllabus, and don't forget about this module's quiz. In this short video, we reviewed the major differences between quasi-experiments and true or classical experiments. I talked about one of the major hallmarks of classic experiments is the idea of random assignment or randomization. I also went over a number of different forms of classic experiments, ending with the rarely used Solomon 4-group design. I hope you found this video to be very helpful to your understanding of experiments. As usual, please don't hesitate to contact me if any questions come up. Have a great remainder of your week, and I'll see you back here next time for a discussion on internal and external validity in experiments. Peace out.